entropy, and the second law of thermodynamics. In this session, we will explore several key topics related to thermodynamics. We begin with a microscopic calculation of entropy change to understand how individual molecular behavior relates to the system as a whole. From there, we will introduce the entropy statement of the second law and demonstrate the equivalence between the various statements of this law. We will also examine how entropy changes in real-world processes and conclude by discussing the ultimate fate of the universe, often referred to as heat death. To understand entropy from a microscopic perspective, we focus on the arrangement of individual molecules. We define the number of microstates for a single molecule as the volume of the container divided by the microscopic volume of the molecule itself. For a system containing a total number of molecules n, the total number of microstates is found by raising the single molecule value to the power of n. Using this approach, entropy is defined as Boltzmann's constant multiplied by the natural logarithm of the total number of microstates. Let us apply this to an example of free expansion, where a gas moves from an initial volume to a final volume that is 4 times larger. Initially, the microstates are determined by the starting volume. After expansion, the final number of microstates increases because the volume has quadrupled. To find the change in entropy, we take Boltzmann's constant times the natural logarithm of the ratio of final to initial microstates. This simplifies to the number of molecules times Boltzmann's constant times the natural logarithm of 4, which is also equivalent to the number of moles times the ideal gas constant times the natural logarithm of 4. Entropy is what we call a state variable, meaning the change in entropy between two states is the same regardless of the path taken. To demonstrate this, consider a two-step reversible process. First, we have a reversible adiabatic expansion where no heat is transferred, so the change in entropy is 0. Second, we perform a reversible process at a constant volume to return the gas to its original temperature. The entropy change for this second step is calculated as the number of moles times the molar specific heat at constant volume times the natural logarithm of the ratio of the final temperature to the initial temperature. The pressure volume diagram shown here illustrates the two-step reversible process we just discussed. Point A represents our starting state. The red curved line from A to B shows the adiabatic expansion, where the volume increases to 4 times its initial value and the temperature drops from temperature 1 to temperature 2. Then, the vertical line from B to C shows the heating process at a constant volume that brings the gas back up to temperature 1. This path connects the same initial and final states as A free expansion, confirming that the entropy change remains the same. The second law of thermodynamics can be expressed through the entropy statement, which specifies that the entropy of the universe increases in all real processes. Real processes are irreversible and characterized by the continuous spreading of energy. On a microscopic level, this means the universe naturally moves toward macrostates with higher probability. While a perfectly reversible process would result in 0 change in the entropy of the universe, all actual, irreversible processes result in a net increase in universal entropy. We can show that different statements of the second law are equivalent. If the Clausius statement were false, heat could flow spontaneously from a cold object to a hot one without any work being done. This would mean energy is concentrating in the hot reservoir rather than spreading out. Since the concentration of energy represents a decrease in entropy, violating the Clausius statement would directly violate the entropy statement of the second law. Therefore, these two ways of describing thermodynamic limits are fundamentally linked. Another way to show equivalence is by looking at the Kelvin-Planck statement. Imagine an impossible heat engine with 100% efficiency. If we used the work from this engine to drive a heat pump, the net effect would be energy leaving a cold reservoir and entering a hot reservoir without any external work being done. This diagram illustrates how the energy from the hot reservoir flows into the engine, produces work to drive the pump, and results in a net transfer of heat from cold to hot. This violates the Clausius statement and, by extension, the entropy statement of the second law. Let us review entropy changes in different processes. In a free expansion, the change in entropy is the number of moles times the gas constant times the natural logarithm of the volume ratio, which is always positive as energy spreads. In thermal conduction, heat flows from a hot temperature to a cold temperature. The entropy change is the heat transferred multiplied by the difference between the reciprocal of the cold temperature and the reciprocal of the hot temperature, which is also positive. Even in a Carnot cycle, while the engine itself has no entropy change, the entropy of the universe increases due to work overcoming friction. The steady increase of entropy leads to the concept of the heat death of the universe. Because the entropy of the universe increases toward a maximum value, the universe will eventually reach a state of completely uniform temperature and density. At this point, energy will be spread so evenly that no gradients will exist to drive any physical processes. This would mean that all physical, chemical, and biological processes would cease, resulting in a state where no further work can be performed. In summary, entropy is defined microscopically based on the number of available microstates. The second law of thermodynamics dictates that the entropy of the universe must increase in all real, irreversible processes. We have seen that entropy is a state variable, so the change in entropy is independent of the specific path between equilibrium states. Finally, we established that the Clausius, Kelvin-Planck, and entropy statements are all equivalent ways of expressing the fundamental limits of nature. To wrap up, consider these review questions. First, why must we arrive at the same entropy change for a gas, regardless of whether it undergoes a free expansion or a multi-step reversible process between the same two states? Second, describe the net effect on the entropy of the universe when an impossible 100% efficient heat engine is used to drive a heat pump. Thinking through these will help solidify your understanding of how entropy governs the behavior of energy in our universe.